Hi everyone, and welcome to an additional video in chemistry, a virtual chemistry lesson, so to speak. Today I thought I'd talk about redox reactions, reactions that involve a so-called reduction and an oxidation. Since the reactions involve both of these processes, we call them redox for short, and what they really do is it's a so-called transfer of electrons from one substance to another. The picture you see here is a magnesium ribbon that's been ignited using a Bunsen burner, and we're going to go into the details of what happens here. So, if we ignite a magnesium ribbon like this, two reactions occur. When it's hot enough, magnesium atoms will react with oxygen in the air, oxygen gas, and nitrogen in the air, nitrogen gas. I'd like you to pause the video and try and write these reaction formulae on your own, and then I'll write both up for you. So here you have them. Are they balanced the same way that you got in your own notebook? Well, I hope so. But it's very important here that we have a balanced reaction, so the stoichiometric coefficients here make sure that we don't have more atoms of one side or the other than the other. So two reactions here, magnesium reacting with oxygen gas and nitrogen gas. And we're going to see what happens more closely when these react with each other. So let's start with the reaction between magnesium and oxygen gas. After the chemical bonding course, you're supposed to know quite a few things. And among those, it's the chemical bonding section of the course. It's not the complete course, sorry. So after the chemical bonding section of the course, you should know that metals and nonmetals combine in reactions to form ionic compounds, which we in layman terms like to call like salts. Magnesium atoms donate 2 valence electrons and form magnesium 2 plus ions. You're supposed to know that magnesium, being in group 2 of the periodic table, has 2 valence electrons, and in order to reach a noble gas configuration, it's easier to donate than to take up electrons. Oxygen is in group 16 of the periodic table, and therefore oxygen need to acquire additional electrons to reach a noble gas configuration. And when an oxygen atom acquires 2 additional valence electrons, well, each of those valence electrons carry a negative charge, so we will form O2 minus. And if we combine positive and negative ions in an ionic compound, the net charge, the overall charge, is supposed to be 0, and that's based on how these substances react. So we're going to look at that. So we're going to look at the Lewis structures. That's an easy way of illustrating the electrons. Here you have the Lewis structure of magnesium. It has 2. And here we have the Lewis structure of oxygen to the right. So magnesium here and the oxygen molecule here, because this is a molecule, right? You see a lowercase number here indicating that we have intramolecular bonding going on. So each oxygen has access to 8 valence electrons because they have their free pairs, that's 4. And then they have 4 additional electrons through this double bond. But if you think about this, the oxygens only actually own, so to speak, 2 of the electrons in this bond because they've shared 2 of their own. So this oxygen atom carries 2 free pairs, and then 2 of the electrons in the bond is its own. So it actually has 6. And that's what you will see if you look in the periodic table as well. Oxygen atoms are supposed to have 6 electrons of their own because they're in group 16. Same thing goes for the other oxygen atom that combine into this oxygen molecule. So both of these oxygens have 6 of their own valence electrons, but then they share 2 of them to get access to a few more. So if we think that we have one magnesium atom here that comes into contact with one oxygen molecule, it has the opportunity to donate its electrons and reach a noble gas configuration, like so. So if this magnesium atom donates its valence electrons, only one of the oxygen atoms will reach a noble gas configuration. like so. We'll end up with something along these lines right here. We have a happy, quotation marks, because they can't feel, right? But a happy magnesium ion, a happy oxide ion, right? And a unhappy oxygen molecule, because this poor guy has not reached a noble gas configuration yet. So this is unlikely to happen, because this oxygen, it doesn't get a noble gas configuration, so this won't happen. So we need 2 magnesium for every oxygen molecule. This magnesium can donate to the left hand atom, and this can donate to the right hand atom of the oxygen molecule. And then we'll get something that looks like this. Quite a few happy ions here. The magnesium ions have reached a noble gas configuration, and so have the oxygen ions, right? Or sorry, oxide ions right here. So that's why we need 2 magnesiums for every oxygen molecule. And since ions are formed as the product and compounds are formed, we know that this involves a transfer of electrons. Let's look at this very same thing, but we write it using a reaction formula instead. Then we would write it like this. We need 2 magnesium. They're in the solid state at room temperature. They react with oxygen gas in the room. So this will be in gaseous form. And they will form magnesium oxide, which is a salt, and they have typically very high melting points, so it's bound to be a solid as well. 4 electrons were transferred from the magnesium to the oxygen molecule, like so. And we can feel free to write an arrow like this to indicate the flow of electrons. That's something that we want you to do eventually in future exercises. So we have deduced that 4 electrons will be transferred, and therefore we will form 2 units of magnesium oxide. Remember, we only write the lowest, smallest ratio we can have here. In reality, we have billions upon billions of these being formed, if we have anything that we can see in size. But yeah, we write the empirical formula of every species here, and the smallest coefficients we can to keep it simple. So the simplest ratios are shown. Magnesium. The magnesium loses its electrons in this. And in chemistry, the process of losing electrons, that's called oxidation. So we say that this substance is oxidized. The oxygen, on the other hand, it accepts or steals or gains electrons. And then we say that this is a reduction of the oxygen molecule. So this substance is reduced. So these terms are essential for reduction oxidation, because if you mix them up, then you're going to get all your answers wrong. So a mnemonic for this is the so-called OILRIG. So this allows you to memorize what is oxidation and what is reduction. So whenever you think about this, think about an OILRIG like this, and then you think about this. Oxidation is loss of electrons, so OIL, oil, and reduction is gain, RIG, like that. So if you memorize this rule or this mnemonic, then you're likely to remember what they mean. So there was an additional reaction going on here, right? Magnesium reacted with nitrogen gas. So I'd like you to determine what's oxidized and what's reduced in the reaction between these species. So do that now. So this is fairly similar to the previous example. You know that nitrogen, it's in group 15, it needs additional valence electrons. Each nitrogen requires 3, and they're stuck in an N2 molecule, so they're going to need a total of 2 times 3, which is 6. So we're going to need a transfer of 6 electrons here. For that we need 3 magnesium, because each magnesium donates 2. Since magnesium in this example as well donates the electrons or loses them, it's oxidized. And since the nitrogen gains electrons, it's reduced. All right. Another very important concept when we talk about the basics of this are so-called half equations. Half equations, they are halves of redox reactions, because these reactions that involve both oxidation and reduction are called redox reactions. And then sometimes we just need to go into the details of what is actually oxidized and what is actually reduced. Then we write so-called half equations. The overall redox reaction, we wrote that before, it's this. This involves both the thing being oxidized and the thing being reduced. If we look at the oxidation half equation, we only look at what's oxidized. In this case, magnesium was oxidized and formed magnesium ions like this. And when 3 magnesium form 3 magnesium ions, we get 6 electrons being given away or lost. For the reduction, well, the nitrogen needs to take up electrons to form the nitride ion, and they need to take up 6 electrons like this. So now you actually need to write out electrons when you write equations like this. And a very important rule here is that the number of electrons lost are the number of electrons gained. So if magnesium in this reaction will give away 6 electrons, then 6 electrons will be taken up by the nitrogen gas. So this needs to be the same number of electrons here. Yeah, so the number lost must be equal to the number gained of electrons now. So what are half equations good for? Well, they're good for showcasing what's oxidized and what's reduced and the number of electrons involved. But they're also useful, for example, when it comes to balancing reaction formulae. So let's look at the reaction between aluminium and iodine. And what we do then, if we don't know how to balance this in the classical method that we've done before, we still know that aluminium needs to donate 3 electrons because of its group number. So that will be, and since it's a metal and donates electrons, this will be the oxidation half equation here that I've written to the right. Each aluminium donates 3 electrons to form an aluminium 3+ ion. And iodine needs to gain 1 electron. Since they're stuck together 2 by 2 in the iodine molecule, we're going to need 2 electrons to form 2 iodide ions, like so. Now, in order to balance these equations, we look at the number of electrons between both. In the first one, we had 3 electrons being donated or lost, and in the second one, we had 2 electrons gained. These need to be the same number, so find the lowest common denominator, and then we multiply both expressions. So the lowest common denominator is 6, so if you take this times 2, then you will find the following, that 2 aluminium will form 2 aluminium ions plus 6 electrons, like so. The reduction half equation, well, we need to take 3 times the previous formula, so we then add 3 times 2 is 6, and 3 times 2 is 6. So 3 iodine take up 6 electrons to form 6 iodide ions. Now we have the same number of electrons for both. And then we can sum these equations up together. What we do then is that we take everything before the arrows for both the reactions and put them next to each other, like this. So we take everything before that arrow, and we take everything before this arrow. We sum up everything. We can move down one of the arrows like this if we have access to animations. And then we add everything we have after the arrows as well. So now we combine these two half equations into one big equation like so. And here I've written it a little bit more cleanly. So Now we can do the following. If we have the same thing on both sides of the arrow, we can remove it. It's just like math. So in this case, we have 6 electrons before and after. So these two can be removed. Then we end up with the following expression. It's not very neat at the moment. We like to clean this up. We want to combine the ions here into the ionic compound. That's usually how we write it. And we want to add states of matter. So this becomes the following. Aluminium, well, it's a metal, so it's solid in room temperature. If you're my student, then you've done some experiments with iodine, and then you know that that's a solid as well. And then the product that forms will be aluminium iodide, like this, and that's going to be a salt, high melting point, so we can assume solid. Maybe this reaction needs a little bit of help. Maybe we need to heat it so the iodide would actually be in gaseous form, but that's maybe not the focus of this video. Just a thought. All right, so that's how we used half equations to balance equations. For many of you, that might seem a little bit unnecessary because you know how to balance equations already. But we're going to build on that at the end of the redox part of the course, and then you will definitely see how useful it is to balance complicated formulae. But we'll get there. For now, I'd like to introduce some additional terms, more terminology, and I'd like to introduce the concepts of oxidizing agents and reducing agents. The example I will use here is the formation of rust. The formation of rust is not just one reaction, it's quite a few. There's iron reacting with both hydroxides and oxides and so on, and a vast mix of it. But for now, let's simplify it and just say that it's formed when iron reacts with oxygen. And iron reacting with oxygen will react according to this formula here. And this then is our rust, the iron oxide here. If you use the principles we've gone through, you will see that we need 12 electrons being transferred from iron to oxygen. Why? Well, that's because if you look over here, we can see that the iron will have a 3+ charge in this compound. Each oxygen has a 2- charge. We have 3 of them, so 2 times 3 is -6. Then each of the irons must have a +3 charge here. So we need a total of 4 iron here, and if each iron gives away 3, that corresponds to 12 electrons as well. So the interesting part here is that if we had no oxygen at all, well, then the iron would not react with oxygen. So we then say that the oxygen sort of causes the iron to be oxidized. So since the oxygen helps iron being oxidized, oxygen itself is a so-called oxidizing agent, something that helps helps another substance being oxidized. We can turn this around. If we didn't have iron atoms available for this oxygen, then it would not react this way. So the iron causes the oxygen to be reduced in this reaction. Then we say that since iron helps, it's a reducing agent. It's a substance that causes another substance to be reduced. So here I have those two terms and their definitions. An oxidizing agent is a substance that causes another substance to be oxidized. And a reducing agent is a substance that causes another substance to be reduced. The oxidizing agent will itself be reduced, right? If it forces something to be oxidized, well, then it must take those electrons for itself, and the reducing agent will itself be oxidized. So whenever something is oxidized, you know that it's also a reducing agent, and whenever something is reduced, you know that it is an oxidizing agent. Don't blame me for the terminology. This is standard in chemistry, so we have to learn it. And when we talk about oxidizing and reducing agents, it's not just either or, it's relative strengths. So we can talk about strong oxidizing agents or weak oxidizing agents. For example, potassium permanganate is a strong oxidizing agent, whereas the iodine is a weaker oxidizing agent. And the stronger the oxidizing agent is, the better it is at forcing another substance to be oxidized. Useful for quite a few chemical reactions if we want to oxidize, for example, molecules, turn alcohols into carboxylic acids and stuff like that. And I mean, we can say the same thing about reducing agents. The stronger they are, the better they are at forcing something else to be reduced. So, and this is related to how reactive they are. If we have a strong oxidizing agent, it has a high tendency to become reduced itself, so it's a reactive substance. So the more reactive they are, in one way or the other, there will probably be a strong oxidizing agent or a strong reducing agent. And then a final part of the terminology that I'm going to introduce today is so-called the reduced or oxidized form of elements and substances. So it might be good for you to distinguish between elements in their reduced form and their oxidized form, and this differs between metals and non-metals. So let's look at how iron reacts in chemical reactions. Well, it can either give away 2 electrons or 3 electrons, dependent on the chemical reaction at hand. Remember that iron is a transition metal, so it doesn't quite follow the rules we've learned throughout the course. The number of electrons may differ a little bit, but these are the common versions of iron that we have here. And I've added double arrows just to indicate what happens if the reaction goes back the other way. So, when iron reacts, we form positive ions, right? And we do that by losing electrons. Losing electrons means oxidation, right? So in order to form these ions, we need an oxidation. So that's why we say the iron ion is in its oxidized form. And if we think about going the other way, if we have iron taking up electrons, iron ions taking up electrons, so we go to the left in this reaction here to form iron, well, then that process of taking up electrons, that's reduction, right? So going to the left here, we have a reduction process. So iron as an element will be in its reduced form. And it doesn't matter which one of these we look at. So that's how I usually like to reason when I try to remember what's oxidized and what's reduced form. Here you have a few examples of reactions. So let's see what happens here. We have oxygen gas when, I've added states of matter here for some reason, but yeah, you don't need that. Actually, there we go. Now I fixed it. So, because let's not clutter this too much. So, oxygen comes as an oxygen gas usually, right? So, in order for oxygen to form oxide ions, we need to take up extra electrons to gain a negative charge. And this process of taking up electrons and forming something with a negative charge, well, gaining electrons is a reduction. So what we have on the right-hand side here is the reduced form. That means if we think about this in the other way, if this oxide ions, if these oxide ions react back to form oxygen and giving away electrons, well, giving away electrons, that's a oxidation. The same thing can be said about this sulfur here. If it gains electrons and turns into a negative ion, it will be reduced because it gained electrons. If these sulfide ions, react back, well, then we will have an oxidation, right? Because we give away electrons again. And both of these are possible, dependent on the type of chemical reaction that we use. Aluminium then. Well, if aluminium reacts, it typically forms aluminium ions. That process involves giving away electrons. Losing electrons is oxidation. So then we write the oxidized form here because this is what's formed during an oxidation. If aluminium ions take up additional electrons, well, then we will have a reduction, and that's the reduced form. And the same thing can be said about sodium when sodium reacts. Reduced form and oxidized form, like so. So, note that metals react to form ions via oxidation. And the more reactive the metal is, the better the reducing agent it will be. And note that nonmetals react to form ions via reduction. And the more reactive they are, the better the oxidizing agent they are. And that's it for me. I hope you learned something today, and I will see you in another video.